I'm not listing them all out, but basically we're going to look at how rates of reactions are changing with concentration and temperature, the additions of a catalyst, like that. So when we're thinking about chemical reactions, they're quite complicated. There's a lot of things that we have to consider in order to really understand what's happening in a chemical reaction. You need to understand the reactants and products. Okay? What species are transforming? Okay? What are reacting? What's being formed? So you saw that in chapter 3. And also in chapter 3, you learned about stoichiometry, so you're relating the amounts of reactants and products with stoichiometry. Chapter 5, you looked at the energy of reaction. Exothermic, endothermic came into play, delta H. We will get to spontaneity, which is chapter 19. I'm bringing it up again, simply to state that a reaction may be spontaneous, but it doesn't have to be fast. So those things are not automatically the same thing, okay? So spontaneous doesn't necessarily mean fast. We'll cover this in much more detail in chapter 19. And then the one other thing, and that's this chapter, we're going to look at rates of reactions. So how fast does a reaction occur? So again, spontaneous does not necessarily mean fast, but we do need reactions to occur at a useful rate in order for them to be useful, or a fast enough rate in order for them to be useful. So this reaction is the formation of ammonia. It is a spontaneous reaction, but it does not occur very quickly at 25 degrees Celsius in 1 atmosphere. This reaction is really important because it's useful in terms of making fertilizer. And so there's a very famous German chemist, last name is Haber. You may have seen this name before. The Haber process basically takes this reaction and adds an iron catalyst to make this reaction occur much more quickly. And so we can produce ammonia, use it with fertilizer, and we can all eat, basically, is what it comes down to. The Wikipedia page on Fritz Haber is quite a good read if you are up late at night and you've got nothing better to do. Check that one out. Okay. So, chemical kinetics. All right, studying the rates of reactions, the steps involved in a reaction, and reaction mechanisms. So by which bonds are being broken, which bonds are being made. And that's going to be involved in the reaction mechanisms. There are several factors that are going to affect our reaction rates. Concentration, the physical state of the reactant, solid, liquid, gas. The particle size of reactants is going to be important. We saw this actually, was it Friday, when we did the vapor pressure lowering demo, where I had what sodium salt was it? I don't even remember. The sodium salt was in a sort of large chunks, and it took a long time for that reaction to occur, and so we didn't see the outcome until a few minutes later. If we had ground up that salt and then let that happen, it would have occurred much more quickly. Temperature is important. We're going to see the relationship there. And then the use of catalysts. So a catalyst is something that makes a reaction proceed faster, but isn't used up in the reaction. They're pretty cool how they work, so we'll talk about that later at the end of the chapter. So the main sort of line of thinking that you want to have, and when you're relating how all of these variables affect reaction rates, is with the collisions between reactants. Okay, I think I want to switch to my next slide here. So we use what we call collision theory. Which basically just says if you have a greater frequency of collisions, the reaction occurs faster. Okay, here's another shorthand for you. Rxn is reaction. Okay, so be thinking about collisions between reactants. All right. Now, in your notes, what do you expect to be faster? Take a look at each of these things. Make an educated guess based on thinking about collisions. Which is faster? Higher, lower concentration, higher, lower temperature, solid, liquid, or gas, particle size. Let's take a couple seconds here, make a guess. Okay, so in terms of concentration, if we're thinking about collisions in a container of some kind, a container with a higher concentration of reactants will lead to a faster reaction rate. Okay? More molecules able to react with each other, faster. What about temperature? Higher. Okay, so at a higher temperature, molecules are moving around faster in a container. Okay, so they have a greater probability of colliding with one another. I'm going to write this down. Moving faster. The other really important thing with temperature is when we increase the temperature, we increase the energy that those molecules have. So they're going to have a greater energy when they collide. What that's going to do is allow the reactions to occur at a faster rate. And we're going to talk about activation energy and things like that. And you'll see how basically we have to get over a hill. Okay? And if you have something with greater energy, it's easier to get over the hill. Physical state. Solid, liquid, or gas, which is going to occur fastest? Gas. Okay? Our molecules are moving around. More collisions are possible. Okay? Particle size, I mentioned this, so small particles are going to allow for reactions to occur at a faster rate. All right. And then, as I mentioned before, just simply the presence of a catalyst increases the rate of reaction.
So will small particles react faster just because there's less of them?
Small particles react faster, and it's related to surface area.
Okay.
So if there's a greater surface area with the smaller particles, so same amount, greater surface area, they react faster. Okay, so look at these three containers. There's solids, gases. Which vessel has the reaction that's going to occur the fastest? Take a quick note there. Yeah, see a couple of twos. I think this one might be kind of obvious, which is good. We want it to be obvious. Okay, so in the second box, middle box, we have a higher concentration of gaseous molecules. Gas also in 3, but the concentration is lower. The solid, you can see just by the picture that it's very hard for the red and the blue to interact. Okay, we're assuming those are reactants. Okay. All right, this is just basically a statement here on what a reaction rate is. So we're going to see how the disappearance of reactants and the appearance of products are related to the reaction stoichiometry. Okay, so we need to have balanced chemical equations in order to do these problems. And so the reaction rate is going to relate stoichiometry and rate, and the disappearance and appearance. let's take a look here in general about a reaction that's going to take place. We're going to have C4H9Cl. It's going to react with water and form some products. Okay. I want to note a couple things. On our y-axis, I'm going to write this horizontally. We have in brackets C4H9Cl. I want to point out you're going to see brackets a lot. And what the brackets are going to mean is the concentration of whatever is inside of brackets. Okay. So on our y-axis, we have concentration of C4H9Cl. On the x-axis, we have time. And what we're going to see happen is if we monitor the concentration of C4H9Cl over time, we are going to see the concentration decrease as the reaction proceeds. And another thing that is important to note is that the initial reaction at the beginning, the concentration at the beginning, no, sorry. The rate at the beginning of the reaction is faster than it is later in the reaction. And we're going to talk about why this is and how to measure that. For right now, it's fine to see, and this is important, that a steeper slope, this versus this, means a faster reaction rate. Okay. Okay, so I want you to again make a prediction. We've got a plot here of the concentration of X on Y versus time. And there's two things I want you to figure out based on what our options are here. Okay? Is X a reactant or a product? And is the reaction rate speeding up or slowing down? Okay. So take a look at that, just based on the figure. Discuss with your neighbor. See if you come up with the same answer.
The variables, can they does one trump the other? Will a higher concentration liquid react faster than a lower concentration gas?
That's a very good possibility that happens.
It does?
Yeah.
Is there just kind of you just hope they're far enough apart that you know? Or...
The examples I gave were just sort of in general.
Okay.
But yeah. Well, I don't think we're going to ever see... I don't think you're going to ever have to make that decision.
Okay, because I know with IMF, obviously there's stronger, H bonding is stronger than dispersion,
Right.
so I figured that there was some correlation between those two.
Right.
Okay, so we probably shouldn't have to worry about which is stronger than
I
the
don't
other.
think so.
Okay, and are we given the solubility rules on the exam, do you know? Or no, we're not?
No.
Okay.
All right. So, hopefully you came up with D. All right. X should be a product. We've got basically nothing to begin with. We're forming products, so the concentration increases. If we look at the reaction rate based on the slopes of the lines, if you draw tangent lines, the reaction is actually slowing down. Okay. All right. So let's take a look at how we are able to relate reaction rate and stoichiometry. We'll go back to our C4H9Cl example. We can actually look at how the reaction rate is changing based on the disappearance of reactants or the appearance of products. So either way is fine. I think I've got another, yeah. So for example, the rate for this reaction is given by the change, which is delta. Change in concentration of C4H9Cl over the change in time. Okay. And we put a negative sign out front of any reactant, where we're relating the reactant concentration to the rate. And the reason is simply that we know that the concentration is going away, because it's the reactant is reacting away. Because so when we actually look at doing the math here, I'm going to just abbreviate. The change in concentration is going to be equal to the concentration of that substance. I guess we can use X. We'll say final minus initial, or time 2 minus time 1, you're going to see later on. And so if the concentration is decreasing with time, this factor ends up being a negative. So if we put a negative out front of our rate equation, that just makes it a positive number. We always state rates as positive numbers. Okay? Yeah, cool. Okay. We can do this for any type of equation, reaction equation. Let's say we have the general expression, general reaction, A plus B yields C plus D, where lowercase a, b, c, and d are our stoichiometric coefficients. The rate with respect to A, reactant A, is going to be minus 1 over the stoichiometric coefficient times the change in concentration in A over the change in time. Okay, so it's always going to be 1 over the stoichiometric coefficient. Okay, that's the way to remember that. Again, negative signs for reactants. And we don't put a negative sign for products. Okay, so those are going to be positive values. Okay, questions on this? Yes.
What is the stoichiometric coefficient?
So, for instance, in our equation up here with actual things, it's just going to be the number in front. Yep. And you don't see it when it's 1, right? So this is really minus 1 over 1, which is 1. Okay, so here's another example. We've got 2HI forming H2 and I2. So what is the rate of formation of H2? And so I'll start you out here. Rate equals. So we're going to use our stoichiometric coefficient, 1 over the stoichiometric coefficient. H2, there's 1 H2 in our equation, times the change in concentration of H2 over the change in time. Okay. And then, let's see. You can see on our plot as well how this is going to play out in terms of stoichiometry. So for our products, they both have the same stoichiometric coefficient of 1. And so the formation of those is going to follow the same line shape, okay? Same curve. So not only do they have very similar rates, so the rate of formation of I2 is the change in concentration of I2 over the change in time, but they look the same in their curves, okay? That doesn't mean that there's only like one product being formed, it just means that there's two lines over top of each other. Yes?
Are there any reactants that break that rule? So like, maybe they start out slow, but for whatever reason, it speeds up?
Are there any reactants where the reaction starts out slow but then speeds up? Not that I can think of, but that doesn't mean there isn't one. It's probably a very special case. Okay, so it's a little hard to see on this figure, but the disappearance of HI occurs at twice the rate of the appearance of H2 in I2. And if we write out our rate for the disappearance of HI, again, we're going to use 1 over our stoichiometric coefficient, which is 2, times the change in HI concentration over the change in time. And we're going to be able to relate this to the formation of one or both products, but let's just relate it right now to the formation of H2. Okay. And I'm just going to erase this. It's fine if you leave it, but it's easier to see what we're going to do here. We're simply going to multiply both sides of the equation by 2. Okay, to cancel these out on the left side. And so the rate of disappearance of HI is equal to 2 times the appearance of H2 over delta T. See that? Everyone see that? Yes?
Wouldn't the 1/2 be negative?
It is negative. Good point. Anything else? Yes.
So like basically your relationship between the two, I guess, rates is whatever that coefficient is. Like if you're looking at a graph of both the reactants and the products.
Yeah, so the appearance and disappearance are related via the stoichiometry. It's you could just simply set this bottom equation up based on the stoichiometry, but I think it is if you're consistent in saying that's 1 over the stoichiometric coefficient for the thing it's in front of, so 1/2 times HI, it's not as easy to mess things up, because this is harder to arrive at, I think, than the other. Did you have a question? Okay. Everyone okay with that? All right. Oh, so here we are. Okay, so let's look at some actual numbers. So we can say that hydrogen is being produced at a rate of 3 moles per liter per second. And so if that's true, at what rate is iodine being produced? I2. Yeah. 3 moles per liter per second. Okay, we can see that here where the rate of formation of hydrogen is equal to the rate of formation of iodine. There's no stoichiometric coefficients in there. They're both the same, so they're formed at the same rate. Okay. So then what rate is HI being consumed? Yeah, 6 moles per liter per second. Okay, and again, if we multiply both sides by 2, why did I write a question mark? I think that was supposed to be 2 times. There. So we're multiplying, so delta HI over delta T is equal to 2 times, we're going to just look at H2, which was 3 moles per liter per second. Does that make sense? Questions? Okay. All right, so let's just look at a different reaction here. We're going to take 2 NO2, and it's going to form 2 NO and O2. I've given you some concentrations of NO at various times, but for right now, let's just look at what the rate of appearance of O2 is, simply based on our stoichiometry. So rate's going to be equal to the change in the O2 concentration over the change in time. Okay, stoichiometric coefficient of 1. The disappearance of NO2 is going to be 1/2 times the change in concentration of NO2 over change in time. Another way of looking at this is to actually write this out. So if you were to calculate the rate between these 2 times with the data given, you're going to have 1/2 times the concentration of NO2 at 285 seconds minus the concentration of NO2 at 215 seconds divided by the 285 seconds minus the 215 seconds. I didn't actually work out this number. Yeah.
I was just confused because it says NO up there, and down here it's NO2.
Oh, I'm so sorry. You're right. Okay, so let's look at the rate of disappearance of NO2, and let's just ignore that's where you're talking about the NO. Yeah, let's just ignore that for right now. We're not going to actually do any math with this. I just want you to see what this equation looks like. Okay. And what I want you to see here is that this is actually an average rate. It's an average over this time, 285 seconds, or 215 seconds to 285 seconds. This is different than what's called the instantaneous rate, which we will be looking at later. So the instantaneous rate is a rate at a particular instant in time. What's an instant? Very, very, very short amount of time. The way I want you to think about this, let's say you are driving to Cleveland from Columbus. It's about 140 miles, takes about 2 hours. And so your average, let's say you're traveling in a car, I suppose I should specify that. Your average miles per hour would be about 60 miles an hour. Right? But you know that you're not going 60 miles an hour from the time you start to the time you end. Right? At any point in time, you may look at your speedometer and see that you're going 30 miles an hour. Or you're on 71 and you're going 75 miles an hour. And then you see a cop and you're going 68 miles an hour. But those times when you look at your speedometer, that's the instantaneous rate. Okay? But the average rate is this difference, okay, over whatever time it might be. Now, if we're getting really pedantic, we could say that the amount of time that you're looking at the speedometer, there's a change in rate, but let's not go there. Okay. Does that make sense?
It's just like velocity charts and physics.
Okay. A little bit of a summary here. So our units of reaction rate are going to be in moles per liter per second, 99% of the time. For most reactions, if we plot molarity versus time, so concentration versus time, we're going to see that the rate slows down. And that's whether we're looking at the rate of disappearance of reactant or the rate of appearance of product. The instantaneous rate, okay, is that looking at the speedometer. The other way of obtaining the instantaneous rate is if you draw a line tangent to the concentration versus time curve. Okay, so I was kind of showing you that earlier. You will not have to do a calculation, at least on the exam, where you're calculating an instantaneous rate. Average rate, maybe, but not an instantaneous rate. We're not going to have you draw tangents. And so rates can be written in terms of the appearance of products, or the disappearance of reactants, and they're related with the stoichiometry. Okay, so that make sure you feel really comfortable with those things. All right. Where are we? Now, one of the problems with looking at rates in terms of disappearance or appearance, the way we've done it so far, is that reactions are reversible, and as we will see, they will have equilibria. So the rate of formation of product, there's going to be some basically back reaction where we're reforming reactant. Initially, when we put reactants in a vessel, all of that react is only going to be reactant, and so the reactant is going to form product. Okay. Eventually, enough product is going to build up where the reverse reaction occurs, and that's where it gets really hard to measure a rate. So in order to avoid that complication, what we've done is we've developed some rate laws. Okay? And that's the next section here, which is 14.3. So I moved through 14.1 into 14.2 pretty quickly. Rate laws are going to look at the effective concentration on our rate. We're going to see that both the rate law and our rate constants are going to be determined experimentally. And the rate, reaction rate will depend on the concentration of reactants. So for our reaction where we have 2 NO2 forming 2 NO and O2, the rate law is given by rate equals some rate constant K times the concentration of reactant raised to some power N. And so our rate laws are going to completely ignore products. And that's simply because we're measuring the rate where there isn't enough product to affect the reaction. We're doing that on purpose because otherwise it's just complicated. Okay. So a few general statements here. So the reaction rate is going to be dependent on starting conditions. We're going to see some examples where that's true. we can essentially ignore products. That's why in this equation, ClO2 plus OH minus, we just wrote products. Okay, it doesn't really matter what's formed. Okay. So again, if we're writing our rate law expression for this reaction, the rate is going to be equal to the rate constant K times the concentration of reactant 1, this case ClO2, raised to some power m, times the other reactant OH minus raised to some power n. I've been trying in these slides to use cursive K for our rate constant. When we get to chapters 14, 15, 16, we're going to see a different K. It's an uppercase K. Everything in this semester is a K value, I swear. So trying to be clear here, lowercase cursive K is a rate constant. So the rate that is going to be used in this equation is the same rate that we calculated when we did delta change in concentration over time. Okay, it's the same value. These are equal. We are going to be able to determine our rate constants. That's going to be one of the things we calculate or determine from experiment. M and N are the order with respect to those reactants. I think that's there written on the next slide. Yes. So this is again something that we have to determine from experiment. The way that we are going to do so is by doing different experiments with different concentrations of reactants and then determining experimentally the initial rate. So what this data table is showing us is that we have 3 experiments. In the first one, we use 0.06 moles per liter of ClO2, react that with 0.03 moles per liter of OH minus, and we get an initial rate. Then in the second experiment, we change the concentration of ClO2, but we leave the concentration of OH minus the same, and we see what our initial rate ends up being. In the third experiment, let's compare the second experiment to the third experiment. We leave the concentration of ClO2 the same, and we change the concentration of OH minus, and we observe the rate. Okay. So what this allows us to do is determine the order with respect to those reactants. We're going to determine those exponents, M and N, with respect to those reactants. So the idea is, if we want to determine the order with respect to M, which is related to the concentration of ClO2, okay, we're going to change the concentration of ClO2, but leave the concentration of OH minus the same. And so we do that in experiments 1 and 2. If we want to determine N, which is related to the concentration of OH minus, we're going to use experiments 2 and 3, where we leave the concentration of ClO2 the same, and we change the concentration of OH minus, and see what happens. We'll pick up here on Friday.